So today we'll be doing Commonwealth Prelim Paper 2. So for the first question, okay, A1. The diagram shows part of the periodic table and only some of the elements are shown. So give one element which combines with oxygen to form a gas that contributes to acid rain. Okay, when you see acid rain, right, you immediately think of NO2 and SO2. Your nitrogen and sulfur, right, they are your non-metallic oxides, correct? So they are acidic in nature. Okay, so NO2 and SO2, they will contribute to your acid rain. So if you look at the periodic table, right, I'll immediately know that the answer is N. So nitrogen will combine with oxygen to form NO2 gas, which contributes to acid rain. Okay, for part B, which element forms an ion of type X plus which has only 3 completely filled electron shells? Okay, when I see X plus, right, I know that it is a group 1 metal. Because group 1 metal will lose 1 valence electron to form a positive charge ion. Okay, then now, so I'll zoom into group 1. I have either sodium, potassium or rubidium. Okay, then next, this ion has only 3 completely filled electron shell. So your first completely filled electron shell can contain up to a maximum of 2 electrons, followed by 8 and 8. Okay, so 1 valence electron, right, means I add in a 1 here. So this corresponds to potassium. Okay, makes sense, like potassium would lose 1 valence electron to form 288, which has 3 completely filled electron shells. Okay, then for part C, which element has an atom with only 6 electrons? Okay, the keyword here is atoms, because for atoms, right, we know that in an atom, the number of protons is equals to the number of electron, and we also know that every atom has its own unique proton number. Okay, they have their own unique and specific proton number. So we know that this element has 6 protons because it has 6 electrons, right? So there's only one element in the periodic table that has 6 protons, which is your carbon. Okay, can refer to your periodic table to help you do this, to help you to answer this type of question. So carbon. Okay, for part D, which element has a chloride of type XCl2 whose aqueous solution forms a white precipitate on addition of NaOH? Okay, when you see this, right, immediately you link it to a QA type of question. Okay, so XCl2, chloride ion, it has a charge of -1. So it means that my X ion has a charge of 2 plus to form X2 plus. Okay, so from the elements provided, right, which elements will give a charge of 2 plus and also forms white precipitate with NaOH? If you look at your QA table, you realize that it's either calcium or zinc. Both has a charge of 2 plus and they will form white precipitate upon addition of NaOH. So my answer can either be calcium or zinc. Okay? Then for A2, neon, argon, krypton and xenon, they are 4 of the noble gases. Okay, they are monoatomic elements. So part A, what is meant by the term monoatomic? Okay, monoatomic means that these noble gases, right, they exist as single atoms. Okay, so they exist just as xenon, argon, and so on and so forth. They exist just as one single atom. Okay, part B, explain why the noble gases are very unreactive. Another word that they like to use is inert. It means the same thing, it means that it's unreactive. So why, right, is because their outermost shell or valence shell already completely filled with electrons. Okay, we know that for noble gases, right, they have this electronic configuration called the stable noble gas. Electronic configuration. Okay, so such as like 288. Okay, so when they have this stable noble gas electronic configuration, it means that they would not want to disrupt their stability, so they would not accept or give away any electrons. So that's why they are very unreactive or inert. Okay, because their valence shell is already completely filled with electrons. Okay, so from this question, right, you just need to know that the properties of group 0 elements or your noble gases the properties that they have, right, first they are monoatomic, and secondly they are very unreactive or inert. Okay, for part C, right, this is a more concept question. Okay, so it says that a 1 gram sample of one of these compounds contains 0.549 gram of xenon, 0.134 gram of oxygen, and also 0.317 gram of fluorine. Correct? So they ask you to calculate the empirical formula of this compound. So what we do, right, is we create a table. So first step, I list down what are the elements present in the compound. So in this case, there's xenon, oxygen, and fluorine. Okay, take note that when it comes to oxygen and fluorine, right, we are talking about the elements, not the molecules. So we don't use O2 or F2, we use the elements O and F. Okay? Okay, secondly, right, I write down the mass. Okay, so for xenon is 0.549, 0.134, and 0.317. Okay, next, I write down the AR. So 131, 16, and 19. Okay, then I need to calculate the number of moles in terms of moles. Okay, how I calculate the number of moles, right, is I'm using this formula whereby the number of mole is equals to your mass over MR. Okay, so I take the mass to divide by the MR, divide by the AR, I will get 0.004191, then 0.008375, and 0.01668. Okay, these are the number of moles. Okay, the last step, I need to find out what is the relative mole ratio. So how I find out the mole ratio, right, is I take all the numbers divided by the smallest number, which in this case is 0.004191. Okay, I divide 0.004191 by 0.004191, I'll get 1. Then 0.008375 divided by this number will be 2 and 4. Okay, so how I calculate the mole ratio is I find the smallest number, then the rest of the numbers, right, I just divided by the smallest number to get the relative mole ratio. Okay, so my empirical formula will be, there's 1 Xe, so Xe, there's 2 oxygen, so O2, and 4 fluorine, so my empirical formula is XeO2F4. Okay, then next, what extra information is required to deduce the molecular formula of this compound? Okay, the difference between molecular formula and empirical formula, right, is that your molecular formula is kind of your expanded version of the empirical formula. So it tells you how many atoms of each element there are in the compound. Okay, whereas your empirical gives you the simplest or the most reduced ratio. Okay, so the information required, right? I would need the relative molecular mass of the compound, or your molar mass, or the relative formula mass. Okay, so let's say that they tell me that the relative molecular mass of this compound is 478. Okay, so how do I deduce what is the molecular formula of this compound? So what I do, right, first I calculate the MR of the empirical formula, which should give me 239. Okay, then using the relative molecular mass, right, I just 478 divided by your empirical formula mass number, which is 239, it should give me 2. Okay, so from this, right, I know that the molecular formula will be Xe2O4 F8. Okay, so this will be my molecular formula as compared to the empirical formula. It will be empirical formula times 2 for every element. Okay, so part D. For part D, describe and explain how fractional distillation can be used to separate a mixture of these noble gases. Okay, first we need to know what is the concept of fractional distillation. So, okay, basically fractional distillation, right, is the separation fractional distillation is the separation of a liquid mixture. This is the key word. Okay, into different fractions based on their boiling points. Okay, so now that we know what is fractional distillation, we need to describe the steps. So for the first step, right, we need a liquid mixture. So the first thing we need to do is to liquefy the mixture of your noble gases. Make sure it's in the liquid state. Liquefy the mixture. Okay, then next, I will heat or boil the mixture to collect the different fractions. Okay, then I need to state how do I separate, how are these different fractions collected. So it is based on the concept that each fraction or each noble gas, they will condense at different boiling point. Okay, and the noble gas with the lower boiling point will be collected first. So the gas with your lower boiling point will be collected first. Okay, so these are the steps for fractional distillation. First, I must make sure that the mixture is in the liquid state, because separation of a liquid mixture, right? Then next, I boil the mixture to collect the different fractions or your different noble gases based on their different boiling point. And the gas with the lowest boiling point will be collected first. Okay? Then for A3. Okay, A3, right, is a chemical bonding question. Specifically your graphite. your giant covalent structure. So here they show you the structures of graphite and also your boron nitride. Okay, part A. Like graphite, your boron nitride feels slippery to the touch. So explain in terms of bonding and structure why boron nitride feels slippery to the touch. Okay, for this, right, how we explain, we use the SAE structure also. So first up, we state what is the structure. So it has a giant molecular structure. Basically, we are explaining the structure for graphite because they say that boron nitride is just like graphite. So giant molecular structure. Okay, then next, it has weak intermolecular forces of attraction. Between your carbon layers, or between your layers of atoms. Okay, where does these weak intermolecular forces come from, right? Okay, look at this structure of graphite. For graphite, there's two types of forces you need to know. First is within the layers. Okay, within each carbon layer, right, there are strong covalent bonds between your carbon atoms. Okay, within the layer itself, it has very strong covalent bonds between your carbon atoms, but in between the different carbon layers. Okay, so in between the layers is actually held by your weak intermolecular forces of attraction. Okay, so I repeat again. Within each carbon layer, there's actually strong covalent bonds between your carbon atoms. But in between your carbon layers is actually held together by weak intermolecular forces of attraction. Okay, so now we're focusing on the weak IMF forces between your layers of atoms. Then, due to these weak intermolecular forces, right, only a small amount of energy is required to overcome your weak intermolecular forces, or IMF, weak intermolecular forces of attraction. Okay, therefore, your layers of atoms can slide easily over each other. Okay, that's why your boron nitride will feel slippery to the touch, because your layers of atoms, they can slide easily over each other. Okay, so for part B, okay, part B, an isotope of boron is represented by the symbol, can we erase this? It's represented by the symbol of this. Okay, deduce the number of protons and the number of neutrons in this isotope of boron. First up, what's the definition of an isotope? Okay, isotope basically is atoms of the same element, okay, which has the same number of protons but different number of neutrons. Okay, this is the definition of an isotope. So from here, what's the number of protons? Okay, the smaller number will always be your proton number, which is the number of protons, so 5 protons. Okay, then what does your 10 represent? Okay, what does this represent? This is your mass number or your nuclear number. Okay, which your nuclear number essentially is the number of protons plus the number of neutrons. Okay, whereas 5, this is your proton number. photon or atomic number. This is your number of protons. Okay, so to find the number of neutrons, I just 10 minus 5 to get 5 neutrons. Okay, this one is an atomic structure question. Okay, so for part C, explain in terms of bonding and structure again, why graphite has a high melting point. Okay, this is a very classic question. So this is in your notes, chem bonding notes. Okay, so for graphite, right, same thing, I use the SAE structure again. So S stands for structure. I say graphite has a giant molecular structure. Okay, then now for attraction, right? Okay, for graphite and diamond, it's more detailed and you need to know the specific attraction. For graphite, it will be each carbon atom is covalently bonded to 3 other carbon atoms in a each carbon atom is covalently bonded to 3 other carbon atoms in a hexagonal plane arrangement, thus forming an extensive network of strong. We are going to do A4. The flowchart shows some reactions of copper 2 nitrate, CuNO3 2. Okay, so this is the flowchart. Let's look at part A. When copper 2 nitrate is heated strongly, copper oxide A and B are made, and they ask you to write the formula for B. So now let's look at the flow chart. So CuNO3, copper 2 nitrate, upon heating strongly, I have a black solid. Remember, copper oxide is always black, not blue. Okay? Then there's a brown gas and also gas B. Gas B is a colorless gas that relights a glowing splint. So immediately we know that this is oxygen. It is the test for oxygen gas. So the formula for B will be oxygen. Okay, then part 2, construct the equation for the action of heat on copper 2 nitrate. They have already told you what will be formed. Copper oxide A and B. So it will be Cu Okay, so I know that copper 2 nitrate upon heating will form copper oxide and oxygen. So what is A? If I balance out the equation, right, A will be nitrogen dioxide. Okay, then after that I just balance out the equation. Okay, so now for part B, aqueous copper 2 nitrate is warmed with aqueous sodium hydroxide and aluminium powder. What test is this? This is the test for nitrate ions, correct? So, what is C? Okay, copper 2 nitrate upon warming with NaOH and aluminium will give me a colorless gas. During the test for nitrates, right, the gas that will be produced is ammonia gas. Okay, it will turn your moist red litmus paper blue. Okay, so C is ammonia gas. And what is D? D is a light blue precipitate. Okay, when you see light blue, right, immediately you have to think of copper, Cu2+. So, copper 2 nitrate, upon warming with NaOH, I will get copper hydroxide, okay, which is my light blue precipitate. So, D is copper 2 hydroxide. Okay. For part C, they say suggest the name of reagent X and construct the ionic equation with state symbols for the formation of your green precipitate, copper 2 carbonate. So this is in a solid state. Okay, this one is your salts preparation questions. So, first, we need to determine whether copper 2 carbonate, is it a soluble or insoluble salt. So like when they say precipitate, it means that it is insoluble salt, correct? And there's only one method that we use to prepare insoluble salt, which is precipitation. Okay, then now when it comes to the reagents for precipitation method, we always use aqueous solution and aqueous solution. So now, suggest name of reagent X. Let's see the flow chart again. I have copper 2 nitrate, okay, plus reagent X will give me copper 2 carbonate. So copper 2 nitrate is one of my reagent. So CuNO32, this is one of my reagent, correct? It is soluble because remember all nitrates are soluble. So I need another aqueous solution to form my copper 2 carbonate. So what can reagent X be? It can be sodium carbonate. Okay, remember I need a soluble carbonate in order to give me my CuCO3. Okay, so it can be sodium carbonate or basically any soluble carbonate. Okay, so you can say ammonium carbonate or potassium carbonate. Then now for the ionic equation. Okay, so let me write the chemical equation first. CuNO32 equals plus sodium carbonate. It will give me copper 2 carbonate, which is in a solid state, plus 2NaNO3. Correct? This is the chemical equation. So remember how we form ionic equation? There are two rules to follow. The first rule is that anything that's not in the aqueous state, we don't touch. So in this case, it is copper 2 carbonate, so I don't touch. Then for those that's in the aqueous state, I can break it down into the respective ions. So it will be Cu2 plus 2NO3 minus from CuCO3. Remember, I don't touch anything that's not in the aqueous state, plus 2Na plus 2NO3 minus. Correct? So I am going to cancel away the spectator ions, which in this case will be my NO3 minus, Na plus, anything else? Okay, there's nothing else. So my final ionic equation would be Cu2 plus in the aqueous state plus plus carbonate. Same thing, equals to form copper carbonate. Yeah, this is my ionic equation. Okay? For question 5, ozone molecules are continually being broken down and formed in the upper atmosphere. So this is the equation that shows you how your ozone is being formed, and it has a enthalpy change of minus 392 kilojoules per mole. Okay, when we see negative sign, right, we know that it must be an exothermic reaction. So part 1, explain in terms of bond breaking and bond forming why this reaction is exothermic. Okay, first and foremost, right, exothermic, what's the meaning of exothermic? It means that there is a release of energy to the surroundings. Correct? So how we explain this kind of question, right, is first we say, okay, we use this formula. Your enthalpy change is equals to bond breaking minus bond forming. Correct? So we know that your enthalpy change is negative. So the first thing we say is the energy absorbed to break bonds. Okay, we must see where are we breaking the bonds in. We are breaking the bonds in O2. Correct? So the energy absorbed to break bonds in O2 is less than the energy released to form bonds. To form bonds in where? In our product, in O3. Okay, so we say energy absorbed to break bonds in oxygen is less than the energy released to form bonds in O3. Okay, therefore there will be a net release of energy. Okay, for question part 2, right, they say when 1 mole of oxygen molecules reacts, 392 kilojoules of energy is being released, and they ask you to calculate the amount of energy released when 48 grams of oxygen molecules react. Okay, so first thing first, oxygen molecules is O2. Okay, so I have the mass, I have O2. Can I calculate the number of moles of oxygen molecules? Can, right? So I use the formula which is mass over AR. So the mass is 48 divided by 32. Okay, your MR is 16 times 2, which is 32. Okay, so I will get 1.5 mole. Correct? Okay, then now, the question says when 1 mole of O2 molecules reacts, right, it releases 392 kilojoules of energy. So 1.5 mole of oxygen would release 392 times 1.5 mole, which should give me 588 kilojoules of energy release. Okay, so the energy release is 588. Okay, then now part B. Name a substance that depletes ozone in the upper atmosphere. Okay, there's a few that you can choose from. So the first one you can write chlorofluorocarbons, which is your CFCs. Okay, or your chlorine radicals. You can also write oxides of nitrogen. Okay, for question 6, right, they say the diagram shows this experimental setup. From this setup, I know that it is an electrolysis question. Okay, so now, if you notice this diagram, right, it's separated into cell 1 and also cell 2. Okay, so 2 different cells. Okay, now let's focus on cell 2. For cell 2, right, I have zinc electrode and also silver electrode. Immediately, I know that this must be a simple cell. Okay, the concept behind simple cell is that there will be a voltage produced due to a difference in reactivities of 2 metals. This is the concept of simple cell. There must be 2 different metals with different reactivities in order for a voltage to flow through. Okay, so now let's focus on part 1. They say state the negative electrode found in cell 2 and give a reason for your answer. Okay, cell 2 is a simple cell, and for simple cells, right, which is your negative electrode and which is your positive electrode? Okay, this is the general rule of thumb. For simple cells, right, your more reactive metal will always be your negative electrodes. Okay, so in simple cell, this will be your anode. Okay, whereas the less reactive metal is your positive electrode or your cathode. Okay, why is the more reactive metal your negative electrode, right? Because your more reactive metal tends to gives away electrons more readily as compared to a less reactive metal. That's why it will take on the negative electrode. Okay, so in this case, zinc and silver, which is the more reactive metal and which is the less reactive metal? Zinc will be your more reactive metal and silver will be your less reactive metal. So, what's the answer for part 1? The negative electrode. Your answer will be zinc. Okay, and then now they ask you to explain. Okay, to explain, right, there's 2 points. The first point, you must say that zinc is more reactive than silver. Okay, therefore, it oxidizes more readily. It oxidizes or gives away electrons more readily. That's why it's the negative electrode or your anode. Okay, remember in simple cell, your negative electrode is your anode. Okay, so for part 2, complete on the diagram in cell 1 this time to show the volume of products collected in tube X and Y. Okay, then label clearly the products collected and they ask you to explain your answer. Okay, cell 1. Okay, in cell 1, this is your electrolytic cell. Okay, so take note the difference. Cell 2 is your simple cell, cell 1 is your electrolytic cell. Okay, so now we focus on electrode X and electrode Y. Electrode X is connected to your silver electrode, which is the cathode. This is your cathode, correct? Your positive electrode. Okay, so your cathode must be connected to your anode, correct? And remember in electrolytic cell, your anode is your positive electrode. Okay, so electrode Y is connected to your zinc, which is the anode or your negative electrode, correct? So your anode must be connected to the cathode. So electrode X is the anode, electrode Y is your cathode. So cathode, right, is negative charge, your negative electrode. Okay, so now that I figured out which is the anode and which is the cathode, let's look at the electrolyte. Okay, your electrolyte is concentrated sodium sulfate solution. So we list down all the available ions, which there is sodium. Okay, I have SO4 2- as well, and I have H plus, OH minus. Correct? Your H plus and OH minus comes from the solution, your aqueous solution. So now that I have all these available ions, right, I have to determine what are my products. So at the anode, which is your positive electrode, it will attract your negative ions or your anions, correct? Whereas for your cathode will attract the positive ions or your cations. Okay, so now let's see. At the anode, which is positive electrode, it will attract your negative ions. So I zoom into this, SO4 2- and OH minus. Which is the negative ion that is preferentially discharged at the anode? Okay, SO4 2- will never be discharged because it is very stable. Okay, so OH minus will be the ion that is preferentially discharged. So we write down the half equation. 4OH minus will form okay, this is the half equation for your anode. Then now look at the cathode. Your cathode will attract your positive ions. So again, we zoom into Na plus and H plus. Again, which ion will be preferentially discharged? It will not be your Na plus because it is a group 1 metal which is very reactive and very stable. So it will not be discharged. So instead, your H plus ion will be preferentially discharged. Okay, so we write down the half equation. Okay, it will form okay, so these are my two half equations. Then now, let's see. Okay, show the volume of products collected in tube X and Y. Your electrode X is my anode, right? So this is X, this is Y. Okay, now the next step I need to do, right, is to balance out my electrons, the number of moles of electrons. So let me write here again. Anode, which is electrode X, is where's your cathode? Correct? So these two are my half equations. Now I need to balance out the number of moles of charges. So in cathode, right, I have 2 moles of electrons, and in anode I have 4 moles of electrons. So in order to balance the number of moles of electrons, I times 2. So my final half equation would be 4H plus 4 electrons to give me 2 moles of hydrogen gas. Okay, so now we compare the number of moles of oxygen gas and hydrogen gas. Okay, so O2 is to H2. I have 1 is to 2 mole ratio, correct? So from this I can tell that the volume of hydrogen gas produced would actually be twice the volume of oxygen gas produced. Okay, so the volume hydrogen gas produced is twice the volume of O2 produced. Oops. Okay, then now I have to draw the volume of products in X and Y. So for X and Y, it will be this is my O2 and this is H2. You can tell that the volume of oxygen, right, is actually half the volume of hydrogen. Okay? So, how do I explain the answer, right? I have to say, okay, I'm going to erase this. Okay, I have to say, for every 4 moles of electrons transferred, 1 mole of O2 gas and 2 moles of hydrogen gas will be produced. Okay, then since the number of moles of gas is proportional to the volume of gas, the volume of H2 produced will be twice the volume of O2 gas. Okay, so the main part here is the number of moles of gas is proportional to the volume of gas. How do we know this, right? It's based on this formula. You know that for all gases, right, 1 mole will occupy 24 dm cube. So the number of moles is always proportional to your volume of gas produced. Okay? Then it's also good if you include your half equations for production of H2 and O2. Okay? Then you'll get get full marks for this. Okay, now for part B. In another separate experiment, your aqueous copper 2 sulfate is electrolyzed using platinum electrodes, which is inert electrodes. Okay, now they say copper 2 ions are reduced to copper at the negative electrode, whereas oxygen is formed at a positive electrode via loss of electrons from hydroxide ions, OH minus. Okay, part 1. Give the formula of all the ions present in aqueous copper 2 sulfate, your CuSO4 aqueous. Okay, so this one, Cu2 plus, SO4 2 minus, H plus and OH minus. Again, your H plus and OH minus comes from the aqueous solution. Okay, then now part 2. Explain why the solution becomes acidic as the electrolysis proceeds. Okay, now all our answers are actually in the question. So let's see. At the negative electrode, okay, at the negative electrode, which is my cathode, right? What is the half equation? It says that copper 2 ions are reduced to copper. So Cu2 plus 2 electron to form Cus. Okay? Then at a positive electrode, which is your anode, your oxygen is formed by loss of electrons from hydroxide ions. So again, 4OH minus. Okay, so these are my half equation. Now, explain why the solutions become acidic. Okay, let's look at the available ions present. Which ions are being discharged? At the cathode, your Cu2 plus is being discharged, correct? And then at the anode, your OH minus is being discharged. What am I left with? I'm left with H plus and SO4 2 minus. So how we explain why the solution becomes acidic? Okay, when it becomes acidic, right, it means that your concentration of H plus ions must be more than the concentration of OH minus ions, correct? This is the concept behind this question. Okay, so how we explain, right? We'll say that as hydroxide ions, they are discharged or oxidized at the anode to form your oxygen gas, right? The concentration of OH minus ions is less than the concentration of H plus ions. So that it means that there's more H plus ions than OH minus ions now. That's why your solution becomes acidic over time. Because your OH minus ions are continuously being discharged at the anode, so it leaves you with H plus ions having a higher concentration than your OH minus ions. Okay? Okay, then for part 3, explain why the blue color of the aqueous copper 2 sulfate fades as the electrolysis proceeds. Okay, this one is a quite popular question, so just take note. Okay, firstly, right, okay, this blue color comes from where? Your CuSO4 is actually a blue solution, correct? It comes from your Cu2 plus ions. Okay, then now as electrolysis proceeds, at the cathode, your Cu2 plus is losing electrons to form your copper solid, correct? So, over here is it contributes to your blue solution. Then, as copper solid is being discharged, right? The copper solid is a pink or reddish brown solid. Correct? So, as electrolysis proceeds, what happens to the concentration of your Cu2 plus ions? Your Cu2 plus, okay. So, as electrolysis proceeds, concentration of Cu2 plus ions will decrease. Correct? Because your Cu2 plus ions are being discharged to form your copper solid. So the concentration of Cu2 plus ions will decrease, resulting in your blue color to fade. Your blue solution will fade. Okay? So this is how you explain for why blue color of the solution fades. Okay, so first point you must say that your copper ions, your Cu2 plus ions are being reduced or discharged at the cathode. Okay, so this is one point. Okay, therefore, your concentration of Cu2 plus ions will decrease. This is your second point. Okay, and this will then cause your blue color to fade. Your conclusion. Okay? Okay, then for question 7. Iodine reacts with chlorine to form iodine chloride. So this is the equation. Okay, they say that iodine chloride, your ICl, it reacts in a similar way to both iodine and chlorine. So part A, sodium reacts with iodine chloride. What is the equation for this reaction? Okay, for this, right? Okay, let's see what is the reaction between sodium and iodine. You will form NaI. Correct? And then if I balance the equation, it will be this. Same thing for sodium react with chlorine. You will form 2NaCl. Okay? So, what will be the reaction between sodium and your iodine chloride? It will be, I will form both NaI and NaCl. So same thing, I need to balance the equation. Okay, so this is the equation between sodium and iodine chloride. Okay, how I derive this, right, is first I write down the equations for the reaction between sodium and iodine and also chlorine, because over here they said ICl, it reacts in a similar way to both iodine and chlorine. Then I deduce what kind of reaction there will be between sodium and ICl. So this will be your answer. This is your equation. Okay, then for part B, iodine chloride, it reacts with ethene. Ethene is your C2H4. So it has this structure. Okay, draw the full structural formula of the product in this reaction. Okay, for this, your ICl reacts with ethene, which is an alkene, right? So it will undergo ICl plus to form an alkane. This. Okay, so this will be my product. For part B, right, it says that iodine chloride, it reacts with ethene. Ethene is a alkene with the formula of C2H4. Okay, so this is how the full structural formula will look like. Okay, then now, draw the full structural formula of the product in this reaction. Okay, so first, what kind of reaction is this? ICl plus what will be my product? What is this reaction? This is a addition reaction. More specifically, addition of halogen or halogenation. Okay, so this is an addition reaction. So, the there's addition of halogens to your alkene to form a alkane. Okay, so your product will be HH, and then I add in I and Cl. Okay, so this will be my answer. This will be the product in this reaction. So take note, when they say full structural formula, right, you really need to draw all the bonds. You can't just write ICl plus C2H4 to give me all this. You must draw out the specific structure. Okay, for part C, iodine chloride reacts with ethane, in this case it's an alkane, in the presence of UV light, ultraviolet light. Okay, deduce the type of reaction that takes place and construct an equation for this reaction. Okay, when we see presence of ultraviolet light, right, we know that this must be a substitution reaction. Okay, anyway, for alkanes, right, it can undergo two types of reactions. Either your combustion, which is when you add in oxygen, right, to produce CO2 and H2O, or substitution reaction. Okay, for substitution reaction, right, you need to add in, okay, your conditions required will be, there must be presence of UV light, and also you must add halogens. Okay, so what type of reaction is this? This is a substitution reaction. Okay, and then now they ask us to write the equation. Okay, ethane has a formula of C2H6. How do I deduce this? I know that for alkenes, right, it has a general formula of CnH2n plus 2. This is the general formula for alkanes. For alkenes, it will be CnH2n. So ethane, right, will be C2H6. So C2H6 plus ICl, okay, it will give me C2H5Cl plus Hi. Okay, you can also do it the other way. So C2H6 plus ICl, I'll get C2H5 iodine plus HCl. Both is acceptable. Okay, as long as you show me that there must be a substitution of one of your halogens in your final product. Okay, so for part D, draw a dot and cross diagram to show a molecule of iodine chloride. And they ask to show only the outer shell electrons, your valence electrons. Okay, first thing that we need to do, right, iodine chloride, ICl, correct? What kind of bonding will this be? How do I know? Iodine is a non-metal. Chlorine similarly is also a non-metal. So non-metal, what kind of compound will it form? It will form a simple covalent compound. Correct? And how we draw the dot and cross diagram for simple covalent compound? It's via sharing of electrons. Okay? Must learn to differentiate between simple covalent compounds and also ionic compounds. For simple covalent compounds, we are sharing electrons, right? But for ionic compounds, we are not sharing electrons, we are transferring electrons. Okay, from metal to non-metal. Okay, so you must know the difference. So anyway, okay, so draw the dot and cross diagram showing only the valence electrons. Now, iodine and chlorine, they are both halogens, meaning that they are all group 7. Group 7 elements, correct? So group 7 elements has how many valence electrons? Both have 7 valence electrons. So now we draw the dot and cross. So let's say this is iodine and this is chlorine. Okay, this overlapping region will be the part where they share electrons. So iodine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay, then now chlorine, same thing. I use dot and cross to differentiate between iodine and chlorine. So 3, 4, 5, 6, 7. Okay, this is the final dot and cross diagram. So that both iodine and chlorine, they obtain the stable noble gas electronic configuration. Okay, both of them now have 8 valence electrons. So they have achieved the stable noble gas configuration. Okay? Okay, now for A8, a sample of 3.36 gram of magnesium carbonate powder, MgCO3, was divided equally into 2 portions. One portion was added into dilute hydrochloric acid, whereas the other portion was added to dilute sulfuric acid. Okay, the volume and concentration of acids used were both 25 cm3 and 5 mol per dm cube respectively. So they show the volume of gas collected over time. Okay, part A. Which graph represents the results for hydrochloric acid? Let's see. I have hydrochloric acid and H2SO4, correct? What's so unique about them? Okay, so I know that HCl is a monobasic acid, correct? Whereas H2SO4 is a dibasic acid. So what's the meaning of monobasic? It means, okay, 1 mole of acid will produce 1 mole of H plus ions, correct? Then for dibasic acid, basically is 1 mole of acid produces 2 moles of H plus ions. Okay? So, which one will have a lower concentration of H plus ions? It will be my monobasic acid, my HCl, correct? Because it only produces 1 mole of H plus ions, whereby H2SO4 produces 2 moles of H plus ions. So your HCl will have a lower concentration of H plus ions, and when a lower concentration of H plus ions, what does it mean? It means that there will be a slower rate of reaction, correct? Remember, a concentration is a factor for speed of reaction. So a lower rate of concentration is represented by a steeper or gentle gradient. It will be a gentle gradient. Okay, so let's look at the graph again. Which one has a gentle gradient, G1 or G2? The answer will be G2, correct? So this is my graph for HCl. So which graph represents results? The answer will be G2, correct? Okay, then they ask you to explain in terms of particle collision. Same thing, you have to say that HCl is a monobasic acid, whereas H2SO4 is a dibasic acid. Then you explain what's the meaning of monobasic acid. Okay, so you link it to concentration, and then in terms of particle collision, right, a lower concentration means that there will be a lower frequency of collisions between your reactant particles, and this in turn will lead to a lower frequency of effective collision, and this will lead to a decrease in rate of reaction. Okay, so that's how you answer this part A. Okay, then now for part B. Okay, another experiment was carried out by adding 2 grams of calcium carbonate, CaCO3. Remember, initially we added magnesium carbonate, correct? Initially you added magnesium carbonate. So now we are adding calcium carbonate. Okay. So same thing, we are using the same volume of sulfuric acid, H2SO4. So they say, sketch the graph you expect to obtain and label it C. And they ask you to explain the shape of your graph. Okay, first let's write down the chemical equation. So calcium carbonate plus H2SO4. You'll give me calcium sulfate, correct, which is in the solid state. This is an insoluble salt, plus CO2 plus H2O, correct? So this is the chemical equation. Now when I see calcium sulfate and I know that it's an insoluble salt, so how would the graph look like? Okay, now I'm going to draw the graph. So initially the concentration, the gradient will be the same as, not graph 2, graph 1, because this is H2SO4, correct? So initially the gradient will be the same because the same acid was being used. Which is H2SO4, correct? So same initial gradient, and also, okay, then it will come to a stop. So this is graph C, calcium carbonate. Okay, now why? So I'm going to explain the first part. The initial speed is the same as G1 because the same acid H2SO4 was used, correct? Then secondly, the volume of gas collected is very little as calcium carbonate will react with your H2SO4 to form an insoluble salt, which is calcium sulfate, which in turn prevents further reaction between your acid and calcium carbonate. Okay, so let's say this is calcium carbonate. As the reaction progresses, I'm forming calcium sulfate, so I will form a insoluble layer. Okay, this is calcium sulfate. So your acid, it can no longer react with your calcium carbonate. Okay? Now for B9, the Haber process produces ammonia from the reaction between nitrogen and hydrogen. So this is the reaction. Okay, a series of experiments were carried out using different temperatures and different catalysts to determine the percentage yield of ammonia after 3 hours, 24 hours and 30 days. So the table shows the results obtained. Then now for part A, transition metals are more effective than main group metals as catalysts. Explain how the information in the table supports this statement. Okay, now let's look at which are the transition metals. So iron is a transition metal, osmium also. So from here, they are all your transition metals, correct? Whereby aluminium, calcium, they are your main group metals. Okay, so now we know what the role of a catalyst is to increase the percentage yield of ammonia, okay, by increasing the rate of reaction, correct? Presence of catalyst. So explain how the information in the table supports this statement. First, let's look at the transition metals. So do they produce a higher percentage yield as compared to your main group metals? Let's look at iron first. At 400 degrees, For osmium, I produce 20%. For iron, I produce 18%. Compared to your main group metals, which is calcium and aluminium, I produce only 3% and 2%. Okay? So yes, it is more effective. And how we use the information, we have to say this. So we have to state that your transition metals, like iron and osmium, they produce a higher percentage yield of ammonia than your main group metals, such as aluminium and calcium. Okay, after, you can either use the 3-hour mark or the 24-hour mark. It will still have a higher percentage. Correct? So, you have to talk about you have to extract data from this now. So, for example, you say at 400 degrees Celsius, if your iron has a percentage yield of 15% more than calcium. Okay, so I'm extracting data from the table to help me support my trend. Okay, then now for part B,